Honorable Chair, distinguished colleagues, good day and thank you to IEEE Census 2024 for giving me the opportunity to present my research today. My name is Youyang from the Institute of Electronic Engineering, China Academy of Engineering Physicals. My presentation will focus suboptimal joint multiparameter estimation for wireless sensor networks over couple mu fading channels, a challenge in wireless modern systems. We will begin with the background and motivation, followed by the system model and the couple mu fading channel model. And then we will delve into the system model and the joint multiparameter estimation for couple mu fading channels. I will explain the maximum likelihood estimation MLE framework and the proposed smarts with efficient searching strategy. Along with the performance bound analysis, we derive the cross-mirror lower bound CRLB to assess the performance of the algorithm. Finally, we will move on to the simulations and performance analysis and conclude with key takeaways. As smart vehicle electronic architectures evolve, the growing number of communication nodes and performance demands pose challenges for traditional wireless systems, including longer cables, increased weight, and higher installation costs. To address this issue, the industry is turning to intra-vehicle wireless sensor networks, IVWSNs, for data transmission and control, offering benefits like reduced costs, greater flexibility, lower weight, and improved safety. These networks have applications not only in vehicles, but also in enclosed environments like satellites, machine tools, and more. The transmission and sensing quality depends heavily on channel characteristics, as shown in the figure. In a narrow and confined enclosed vehicle environment, the dense and unevenly distributed occlusion and reflection creates small-scale line of sight and no line of sight composite channels with rich multipath propagation. This complexity necessitates the specialized channel model tailored for IVWSNs. Conventional models for indoor, outdoor, and bus scenario may not apply directly. As shown in the table, the generalized couple mu distribution model can simplify into several well-known fading models under specific parameter constraints. Furthermore, the research has demonstrated it aligns well with real-world measurement channel data. Thus, it's a powerful tool for characterizing IVWSN channels across various scenarios. After selecting the channel model, the next critical task is to estimate the channel parameters from the measurement data. Accurate parameter estimation is vital for fitting the model effectively, which in turn ensures reliable transmission and accurate sensing. However, the existing moment estimators have low accuracy, and the traditional theoretically optimal MLE has high complexity. To tackle this challenge, we propose a low complexity suboptimal estimator called SMARTS. Next, we will delve into the system model and the couple mu fading channel model. Consider an IVWSN deploying time division multiple access, where a sensor estimates the channel and perform transmission and sensing tasks individually within a single time slot. The channel envelope closely related to channel characteristics, and the probability density function PDF of the normalized envelope R is shown. It seems complex, but the parameters in this expression is clear. For example, in which kappa greater than or equal to 0 is the ratio between the total power of the dominant components and the total power of the scattered components. Mu greater than or equal to 0 is a natural number related to the characteristics of clusters of multipath components. And IV denotes the modified Basel function of the first kernel with order V. The next is the core of this presentation, joint multiparameter estimation for couple mu fading channels. To achieve precise estimations of kappa and mu, we utilize the traditional optimal MLE framework combined with the SNTO algorithm. The objective is to determine kappa and mu values maximizing the likelihood function. Given n samples and define the estimated parameters, we can get the joint likelihood function and formulate the joint MLE problem. Unfortunately, the presence of the modified Bessel function prevents the traditional methods for solving the simultaneous equations from being applicable. The traditional equations cannot be solved analytically, and the exhaustive search method has too high complexity. Notably, the likelihood function is a multimodal likelihood function, which presents a challenge as many methods can only find local peak values. To overcome these difficulties, a novel algorithm SMART is proposed. SMART stands for the Suboptimal Multiparameter Estimation Algorithm for Robust Transmission and Sensing. We designed SMART based on sequential number theoretical optimization, SNTO, and the proposed efficient search strategy. Renowned for its exceptional search efficiency, SNTO is effective in optimization complex multimodal functions and make it suitable for precise estimation. The main idea behind the SNTO is to generate a set of good lattice points, GLPs, uniformly distributed within the search region probability. Compared to randomly scattered points, the fewer GLPs can effectively cover the entire search area. The method then adjusts its search strategy, navigating towards promising regions. By gradually shrinking the search region, the algorithm converges to the optimal point. The proposed SMART, outlined in the slide, incorporates a crucial modified searching strategy to dynamically adjust the size of the set of GLPs as the search region shrinks. Initially, a large number of GLPs cover the entire search region, ensuring rapid convergence. As the search region diminishes, the number of GLPs scales down proportionally, focusing the search on promising regions. The scaling accounts for a trade-off between the sensor computation power and accuracy requirements. The schematical diagram illustrates the iterative process of the SMARTs. And then we conduct the performance analysis. We derive the Cramér lower bound, CRLB, to assess the performance, which is the theoretically lower bound. The CRLB is defined by facial information matrix, so we first calculate it. Although the calculation is complex, the result is straightforward. The next section is simulations and performance analysis. During the simulations, we generate 10,000 samples for each set of kappa mu using the acceptance rejection method and perform 1,000 Monte Carlo simulations. The performance matrix is including mean square errors, MSE, and the Kullback-Leibler KL divergence, which quantifies how the predicted PDF diverges from the ideal PDF. We compare the MSE and the KL divergence performances of SMARTs and its benchmarks. The MSE curves of the SMARTs closely match those of the CRLB, and it outperforms across a wide range of kappa mu values, thereby confirming its accuracy and effectiveness, and thus demonstrating its ability to provide assurance for reliable transmission and sensing. From this slide, we can see that SMART outperforms others in the presence of the noise interference. Its robustness against noise stems from the likelihood function providing more information. Additionally, SMART fits the measurement data more efficiently than benchmarks, which show greater deviations. Notably, the benchmarks yield kappa less than 0, violating the physical constraints, kappa greater than or equal to 0. The final section is the conclusion. This study proposed a suboptimal multiparameter estimation algorithm called smarts for IVWSNs over the couple mule feeding channels, laying the groundwork for transmission and sensing tasks. Taking into account both the cost and computational capabilities of IVWSNs, we leverage the advantages of SNTO and introduce a strategy to adjust the number of candidates points based on the search region size and achieve improved computational efficiency while maintaining accuracy. Simulation and measurement data analysis conclusively demonstrate its superiority, robustness against the noise, and practical applicability. That's all, thank you. Any questions?